So far, we've talked about significance, but you're probably wondering about something called the p-value, which you may have heard about, or associate with significance, and we haven't talked about that at all. So I want to explain what that is and how it relates to significance. And so let's talk through that a little bit. Significance, first of all, so we've talked a bit about this, and you might have noticed that this is a binary description, right? Significance is something that either is or isn't. So we would say the new poll result was or was not significantly different than the previous one, or, the previous few weeks of polls. The p-value, on the other hand, is a number between 0 and 1, right? So it's continuous. It can take a lot of different values between 0 and 1. So any of these numbers that I've just put on the chart here, these are all possible p-values. I just want you to understand that it's a continuous number. It can take any value between 0 and 1, so it's not binary. Where does the p-value come from? Okay, so remember this figure. We looked at our null world. This is, what are all the possibilities if we're assuming that Melvin's polling, if his popularity is fixed at 60%, and we shaded this range here. So remember this, our figure comes from if 60% of the population supports Melvin, what would happen if we repeated our poll many times? Then we put our new poll, we put this dashed line here. And the p-value describes which proportion of this distribution, right? The distribution is this bell-shaped curve. Which proportion of the distribution is as extreme or more than our new poll, that dashed line? So we can see this graphically. So we can actually just shade the area, right? So here we're going to say as extreme or more. So we're going to shade the part of the distribution that is bigger than our new poll. Is that all? Not exactly, because if we said as extreme or more, you can be extreme in two directions, right? You could be more than or less than. So we're also going to make the mirror image of our survey results. So you could be 10 more than this, 60%, which is where we were at 70%. And another way to be that extreme is to be 10 less. So we mirror our survey result to the other side. So that's at 50. And we're going to shade the part of the distribution that is more extreme than 50. So we're going to go more than 70% or less than 50%. So now we're going to add up the proportion of the distribution in the orange regions. Okay, what does that mean? So what we're going to do is we're going to find out, what proportion of our distribution is under each region. And they're identical, they're like twins, and it turns out it's this number. What this means is that about 2% of our observations are in this range of 70% or more, and about 2% of our observations, in this null world are at 50% or lower. So we've got about 2%, and just by convention, instead of talking in percents here, it's usually described, in a number from 0 to 1, where 1 is 100% and 0 is 0%. And then we add those up, right? So we add those together, and we get this number 0.0412. What does that mean? A p-value of 0.0412. It's too many decimal points, but I'm just showing you, I want you to appreciate that it is a continuous number, but it's often silly to include this many decimal points in real life. So around 4% of the time, in other words, we expect to see a poll result as extreme or more than our latest poll, right? So our latest poll was, the one that was 70%. And so to see something that extremely different, from 60% would only happen about 4% of the time. Now you can think of the p-value as a sort of sliding scale of surprise, where we assume that the null hypothesis were true, and then if the p-value is 0, then it would be quite surprising, assuming the null hypothesis. And the bigger it is, it's quite unsurprising. So we've got these cats. We've got a very surprised cat at the 0 end and a very sleepy cat at the 1 end. So it's about how surprised we are in the context where we're assuming that the null hypothesis is true. Now, because of that is such a complicated definition in a lot of ways, right? It's how surprised we'd be if the null hypothesis were true, right? That's wordy, it's technical. Misconceptions about p-values are extremely common, even among scientists. So here are some of the most common ones. People might say the p-value is the probability that the data were generated by chance alone. That's wrong. It might be that the probability that the null hypothesis is false. No. Or the p-value that our alternative hypothesis is true. None of these are correct. So to repeat, the p-value is the probability that we'd see an outcome as extreme or more than our data shows if the null hypothesis were true. Yes, it's very frustrating that it's this wordy, but it just is. I mean, it's just a complicated concept. Now, you might find this a little bit frustrating because of if that's kind of coming through and you're understanding it and you're feeling like, okay, I get it. You might be saying, wait a second, is that even the thing that we want to know? Don't we really want to know which hypothesis is true, right? Like, isn't that the question we're after? I mean, we didn't set out to find out necessarily how compatible, Melvin's latest poll is with the null hypothesis. We really want to know, is the null hypothesis true or is the alternative hypothesis true? Now, that is right. That's often what we want to know, but it's kind of frustrating because for the first, we never tested how likely the null hypothesis is. We never did anything that said, looking at the world, how likely is the null hypothesis to be true? We investigated how compatible our data is with the null hypothesis, which is actually a different question than how likely is the null hypothesis, right? That's subtle, but those are different. And we also didn't test anything about the alternative hypothesis. We didn't say, is our data more likely to have come from the null or the alternative hypothesis? The alternative hypothesis was kind of just like decoratively there. We didn't test anything about it. It kind of wasn't involved in a way in any of the testing that we did or the analyses we ran. So the alternative was kind of just hanging out there. And if we weren't compatible with the null, then we said, okay, we go with the alternative. And another thing is that the alternative hypothesis is quite vague, and there are, in fact, probably an infinite number of possible alternative hypotheses that we didn't distinguish between, because there are so many ways that, in this example of a poll, there's lots of ways that you could not stay the same. You could increase by a small amount or a big amount. You could go down. There's lots of reasons why it might happen. So we really don't have any insight into, which alternative hypothesis is true or why. And if you find this unsatisfying, you're in very good company. Here's a quote from a paper which has a great name, "The Earth is Round, P less than 0.05, which is kind of a classic. And this is from a prominent American statistician and psychologist. And he says, hypothesis testing does not tell us what we want to know. And we so much want to know what we want to know that out of desperation, we never believe that it does. One more time. Hypothesis testing does not tell us what we want to know. And we so much want to know what we want to know that out of desperation, we nevertheless believe that it does. So we scientists know that hypothesis testing actually doesn't answer a lot of the questions that we're actually after. But we want answers to those questions so badly that we get kind of desperate. And sometimes we act like this is the thing that reveals all to us, even though it sort of is an imperfect tool. And so even though, there are a lot of scientists that feel quite frustrated with hypothesis testing, it does persist as, a major, one of our primary tools for investigating hypotheses about the world and, comparing data, taking data from the world and, interpreting them in light of hypotheses that we have. And, one reason I think it's persisted is that hypothesis testing is a tool. And it does have some uses. It is useful for checking how much observations look like just plain old noise, right? Like in the case of our medication experiment, we do just want to know, is it likely that the difference is, is it compatible with the sort of differences that we would just see from the process of randomizing, who goes into which group? That is a, sometimes a useful thing to know. And we also need to make yes, no decisions. And so being able to make a binary decision about significance can be a useful part of decision making, right? Like we often have to decide, do I want to continue to investigate this medication? Does it show enough promise? Is this worth funding more research about? Should I act on this? Now, hypothesis testing alone is not enough usually, and we'll get to that, but it can be useful for when people need a guideline about yes, no sort of criteria, which happens a surprising amount of the time. But one caution about thresholds, right? And this came up too in part 1. So, go back and talk about how we go back and rewatch the video about how categories reduce information if you want a review of this. But here's the idea showing up again. When we use a binary label like significant or not significant, that can distort our thinking and mislead us. So in this example, where Melvin's polling came out at 70%, we said that is not significant. That is significant. We said a 70% poll is significant because it is outside the range of the values we'd expect if he was still truly at 60% support. So could you imagine, this happens, suddenly that gets, released and the pollsters and the news are saying, wow, the polls are showing a huge spike for Melvin after his rousing egg speech, right? And so maybe we go all in and we say the difference is here and it's real and it's because of his egg policy. So what if the poll had been just 2 percentage points lower and we're at 68%, right? That's a really negligible difference. In fact, the difference between 70% and 68% is not a significant difference. It's a really negligible difference. All of a sudden, we are not significant. And because we suddenly shifted to this category of not significant, maybe our political analysts will say, Melvin's egg policy fails to move voters. This town just doesn't care about breakfast anymore. Right? So it can happen sometimes that because of, a very small difference in what actually happened in the polls, can take us from one category to another. And we treat those categories very differently. So we get into this sort of cognitive distortion about how big the difference is between significant and not significant. And that can really lead us into, bizarre misunderstandings and, a strange sensitivity on the exact, what side of this significant boundary are you on? And it can lead us to radically different conclusions, which is not great, right? We want our conclusions not to depend on, something as small as a 1 or 2 percentage point difference here. Resisting this tendency is very hard work, and even professionals fall into this sort of thinking. But if we want to use this tool correctly, we have to remember that it's not a substitute for certainty. It's a tool, but it's not going to completely give us certainty. And if hypothesis testing makes all of your uncertainty go away, then you're missing something about how it works.